Hey everyone, how are you? It's Rohan here, and in this video I will implement a Longformer end-to-end project on this Kaggle competition feedback prize evaluating student writing. And I'll be using Tensorflow for this project. Now let's quickly look at the classification problem in this particular competition. So basically we have a bunch of essays written by kids in the age of around 12 to 18 years old. And in which we have to find word sequences that can be classified as one of the 7 discourse types given in this essay. And what are those discourse types? They are these one: lead, position, claim, counterclaim, rebuttal, evidence, and concluding statement. So lead means, for example, they have given the definition here that it's an introduction that begins with a statistic, a quotation, a description, or some other device to grab the reader's attention and point toward the thesis. Interestingly, this is not present in all the training set data. Around 40% of the IDs do not have a lead. Similarly, position is an opinion or conclusion on the main question. Around almost all the training data has position. However, it is not always at the beginning. And so if you click on this train.csv right in the Kaggle official page, you can see all these discourse type here under this column heading discourse type. So we can see lead, position, evidence, all these things. So they are associated with a particular ID. And this ID actually refers to a text file, and the text files are all in this train folder. So I think we have around 15,000 .txt file, and each file is identified with a particular ID, and that ID is what this first column represent. And yeah, so let's go ahead. So here in this competition, basically we are tasked with giving feedback on argumentative essays written by students. Specifically, our task is to predict the human annotations. This annotation will be done in 2 steps. First, segment each essay into discrete rhetorical and argumentative elements, and then classify each element as one of the 7 discourse types that we just seen. And now quickly go over the basics of the training data here. So we have a bunch of text files and a separate train.csv that we just saw. In the CSV, we get a reference to the text files and then multiple lines per text file with spans indicating a specific discourse type. So if you just look at this train.csv, you will see each single ID is occurring multiple times. And that's because they represent different spans of the same writing. That is, within each .text file, we have different spans, and those spans needed to be classified according to one of the discourse types. And that's the reason we see multiple IDs occurring in the train.csv. And going over these column heading, so ID is the obvious one, ID code for essay response that represent each single .text file. And then discourse ID. So discourse ID is a unique identifier for each discourse element. Basically, each row in the train.csv contains one discourse element, and the discourse ID is what identifies each of these discourse elements. It is different from the ID column in that the ID is the identifier of the full student essay that the discourse element came from. So multiple rows can have the same value for ID, just as what we are discussing, because each of the rows represent actually one unique discourse. So on the other hand, each row in the train.csv will have a different value for the discourse ID because they represent each unique discourse. And then we have a discourse start, which is a character position where discourse element begins in the essay response. Similarly, discourse end is a character position where discourse element ends in the essay response. Discourse text is obviously the text of the discourse element. Discourse type is a type. Discourse type number is an enumerated class level of discourse element. And finally, we have this prediction string, which is this is the word indices for the training sample as required for predictions. Now, one very important part of this competition is the evaluation metric. We need to really understand how this is calculated here because it's slightly not so trivial. So what it says here for the evaluation metric is that if the overlap between the ground truth and prediction is more than 0.5 and the overlap between the prediction and the ground truth is more than 0.5, the prediction is a match and considered a true positive. If multiple matches exist, the match with the highest pair of overlaps is taken. Now let's understand this. The overlap between the ground truth and prediction. This is a measure of how many words in the ground truth match the predicted words. It is calculated as the number of words that appear in both the ground truth and prediction divided by the total number of words in the ground truth. So for example, if the ground truth for a sample contains 10 words, and the model predicts 8 of those words correctly, the overlap between the ground truth and prediction would be 0.8 or 80%. On the other hand, the overlap between the prediction and the ground truth is a measure of how many words in the prediction match the words in the ground truth. It is calculated as the number of words that appear in both the ground truth and the prediction divided by the total number of words in the prediction. For example, if the model predicts 12 words for a sample and 10 of those words match the words in the ground truth, the overlap between the prediction and ground truth would be 0.83 or 83%. So take this example, so it will be much more clearer. So here in this example, ground truth are 1, 2, 3, 4, 5 and prediction is 1, 2, 3. So common indices between the ground truth and prediction are only this 1, 2, 3. That is 3 common indices. So overlap between the ground truth and prediction will be 3 common indices divided by number 5 because I have 5 ground truth. So the first ratio will be 0.6, which is more than 0.5 as required by our criteria. Now we have to calculate the second overlap, which is overlap between the prediction and the ground truth. So again, we have 3 common indices divided by number 3 here because the total number of predictions are only 3. So this gives a ratio of 1, which is again more than 0.5. So since both the overlaps are greater than or equal to 0.5 as required by our evaluation metric criteria, this particular prediction is considered a match or a true positive. So the important point here is that in both, the numerator is the size of the intersection. Both calculations have to be at least 0.5 for the prediction to be considered a hit. These two measures are used together to determine whether a prediction is a true positive or not. By using both measures, the evaluation metric ensures that the predicted words are not only present in the ground truth, but also that the ground truth words are correctly identified by the model. In some cases, there might be multiple matches. If this happens, that is, if multiple matches happen, the competition rules state that the match with the highest pair of overlaps is considered. And the competition rule also says that any unmatched ground truths are false negatives and any unmatched predictions are false positive. This statement means that any ground truth without a corresponding matching prediction is considered a false negative, that is, missed correct prediction, and any prediction without a corresponding matching ground truth is considered a false positive, that is, incorrect prediction. Alright, so that is enough about the introduction to the competition, and now I'm right back into my VS Code with the actual code implementation for TensorFlow Longformer model for this particular project. And initially all my regular imports, nothing special here, and obviously I'll be using transformers from Hugging Face. And here I'm just defining some of the initial constant variable. And then I'm just reading the train.csv with pandas, and this is my train.csv, exactly the one that we saw in the competition page. Important columns are ID, then we have discourse text, discourse type, and prediction string. And now for checking the data sanity, the first thing I'm going to check that the length of these discourse text and the prediction string are same, because that's how they should be based on the description of the training data set. That is, this prediction string just tells me the indices of the discourse text column. So in these two lines, that's what I'm going to do. First, I am going to build two new column names, discourse len and pred len, and with a lambda function. And inside the lambda function, all I'm doing is just splitting the corresponding column, and yeah, that's pretty much it. And then I'm just defining a new column to display which will have only discourse ID, discourse text, discourse type, prediction string, discourse len, and pred len. And then just print the head of this new data frame. So these two are the new columns, and which represents the length of this prediction string column and the discourse text column. And ideally, these two should always be the same. But do we see some discrepancy? That's what we need to check. And for checking that particular condition, that is the equality between my discourse len and pred len, I use this train.query method of function. So this query function allows you to filter rows of the data frame based on a query expression written as a string. It provides a more concise and readable syntax compared to a traditional Boolean indexing, and is particularly helpful when working with large data frame. So with this line here, I filter rows of the data frame where the value in the discourse len column is not equal to the value in the pred len column, and the result will be a new data frame containing only those specified columns as defined here under the calls to display, and only showing rows that meet the condition that I have specified here within the string. And so in this new queried data frame, that is after applying this filter, this data frame has 468 rows. That means we have 468 instances among all the instances of something like this many numbers where the discourse len is not equal to pred len. And there's a reason. Somebody in this competition has explained that what could be the reason for this. I have put a link to this to that particular explanation discussion forum in the Kaggle website for this competition here. You can just go through and check out the discussion. Pretty nice one. All right, let's move ahead. And then next, I'm just plotting for checking the length and frequency and relative position per discourse type. So I have AX1 defined as I'm grouping by discourse type and also taking discourse len because I want to plot the length of the discourse type. Then sort values and then plot. And similarly, I'm doing for the discourse type here as well. Again, group by discourse type and then take discourse type, count, and sort values. So the next one is a count. So if you look at the plot, here is that plot's average number of words per discourse type is the first one, and the second one is frequency of discourse type in all essays. So looking at this, we can see that the evidence is the longest discourse type on average. And then looking at the frequency, we see that the counterclaim and rebuttal, these two types are pretty rare. Next up, I'm just going to plot a bar plot. And the code is right here. My y-axis is a list of discourse type values coming from train discourse type, but I'm only taking the unique values from this trained discourse type with np.unique. And then I'm doing a count on them, count I for I in np.unique. And when you plot it, and other parameters are just pretty standard one, pretty boilerplate code here. So when you plot it, you get this particular discourse type distribution plot. We can see claim, concluding statement, counterclaim, evidence. That was the highest number of rows again. And then I have position, rebuttal, and counterclaim. They are the least number. They are pretty rare. Next up, I'm going to use the Spacey package to display the various segment from the from the discourse type. So what I want to do is something like this. That is, for this entire span of words, this entire span in blue, that is a position. That's my discourse type. Similarly, for this green part, entire green part, it's a claim. That's my discourse type. The claim is a discourse type. So I want to display the few of the text files text according to its span and the way that it was classified as one of the discourse type, and for which I am just going to use this pretty simple code. And I'm just going to use a little util function called display discourse type visualize, and that I have defined in another Python file, util.py. And here is my little util method, display discourse type visualize. First, I am just iterating over each row in the train data frame where the ID column, that is this ID here, matches the given example. An example is coming from the function argument. So for each row, this function extracts the start and the end indices of a discourse segment and its type, and appends a dictionary containing this information to the ends list. So this ENTS, that will be passed to my as an option to the display.render method, which comes from the spacey package itself. So this looping over here, I'm just building that dictionary called ends. So after this looping is done, all I'm doing is reading the text file whose name is the given example, and reads the contents into a variable called data. And then doc2 is another dictionary where I have three things, that is three key value pairs. Text is data, ends is ends, title is example. And then passing these options to the display.render with doc2, style equal to end, options equal to options, manual true, Jupyter true. And when I invoke that particular function on a set of 5 documents, then I get this nice little rendering of the spans of the text in a single document and their corresponding discourse type classification. So this top is the ID of a particular text file, and this is one span which has been classified as lead here. Then this is another span which has been classified as position, and so on. So I do this just for 5 files. And just in case if you're wondering about these display.render, this is a built-in method of the spacey package, and you should definitely check out the documentation. So it takes a couple of arguments. First one is doc, which I'm passing as doc2. This is the doc object to be rendered. This contains the text and any annotations that will be visualized. And the style, this argument is optional, the name of the visualization style to use. Spacey provides several built-in styles such as ENT for named entities or DEP for dependency parser trees. Custom styles can also be defined. And this one option, this is the most important one. This is again an optional argument. And here is where you configure or structure a few other things. So this option is a dictionary of visualization options. The available options depend on the chosen visualization style. For example, for the ENT style, options can include list of entity labels to show, colors to use for each label, and whether or not to show the entity's text level. Options can also include settings for the arrows, fonts, and background of the visualizations. And also I have manual set to true. So in manual mode, the user can edit or add annotations to the visualizations. And finally, Jupyter equal to true. So if it's true, that means the visualization will be rendered inline in a Jupyter notebook. All right, now it's time to define the model. So at the very top of the file, I have already defined the model name, and here I'm using Kaggle AI Longformer base 4096. And you can go to the Hugging Face document for this model and read some basics on this. So here I'm looking at the official page of this model in Hugging Face. Longformer base 4096 is a bird-based model started from the Roberta checkpoint and pre-trained for MLM On long documents, it supports sequence length up to 4096. Longformer uses a combination of sliding window attention and global attention. Global attention is user configured based on the task to allow the model to learn task-specific representations. Please refer to the examples in modeling longformer.py and the paper for more details on how to set global attention. So for this model, there is while using the model, there's a parameter called global attention mask. If you set the global attention mask parameter when calling the Longformer model, you can control which tokens should attend globally to all other tokens and which token should attend locally to a sliding window of neighboring tokens. But in this notebook, I did not add any global attention. All token attend locally to the default sliding window for this particular exercise. So here in these 3 lines, I'm just defining the tokenizer, very boilerplate code here, auto tokenizer from pre-trained, and to that you pass the model name, then defining the config and also the instance of the model. So tf auto model dot from pre-trained model name, and you pass the config as this config, and that's your backbone or the instance of the model. And next up, to decide whether I'm going to use a single GPU or multi-GPU, for that I have a little util function, multi-GPU use. We'll look into that in a second. But before that, first remember, nowadays Kaggle has provided the option to use multiple GPUs. So you can use two GPUs indeed in Kaggle kernel. So that's the reason I built this little function here, which is multi-GPU use. And it's pretty much uses this os.environment CUDA visible devices.count. If equal to 0, that means I'm going to use a single GPU strategy. So that's what I'm doing in the next line. Else, if this count is more than 0, then I am going to use tf.distribute.mirrored strategy. So this os.environment CUDA visible devices is an environment variable used in TensorFlow to specify which GPUs to use for computation. When a TensorFlow is run on a system with multiple GPUs, os.environment CUDA visible devices can be set to a comma-separated list of integers representing the GPU IDs that the program is allowed to use. That means if you want to use 2 GPUs, you will specify 0, 1. If you want to use 3 or 4 GPUs, you will accordingly increase this comma-separated number here. So in this exercise, I'm going to use single strategy because I'm running these both in Kaggle kernel and my local GPU as well. And locally, I have a single 3070. So that's what I have at the very top of this notebook. I have actually defined this environment variable to have a single number that is only 0, representing my single GPU ID. And that's the reason when I execute this multi-GPU use this method inside the notebook, I'm getting single strategy. And next, I'm going to set this notebook to be trained on mixed precision basis. So I'm running this line, tf.config.optimizer.set experimental option auto mixed precision equal to true. So when using Kaggle's P100 GPU, mixed precision does not make a difference. However, if you run this code locally on a recent GPU, using mixed precision gets speed up train time by as much as 2x. So mixed precision training is a technique for training deep neural networks using both lower precision, for example, half precision, and higher precision, that is single precision, floating point numbers. This technique can lead to significant speed ups in training and can reduce memory usage, especially when training large models with many layers. So this line of code, auto mixed precision option, enables TensorFlow to automatically select the best precision format for each tensor during training based on the tensor's dynamic range without requiring manual specification of precision formats for each tensor, which can be time consuming and error prone. Further, mixed precision training can also improve the numerical stability of the training process. Specifically, using lower precision numbers can help avoid numerical underflow, which can occur when using single precision number in deep neural networks with many layers. By using mixed precision training, the numerical stability of the training process can be improved without sacrificing performance. However, it's important to note that not all hardware supports mixed precision training and not all models may benefit from it. Therefore, it's important to experiment with the different precision formats and configurations to determine the optimal approach for a particular model and hardware setup that you are currently running. And before starting the training, I just want to understand a couple of things on my data. That is, the first one is labels. What are the different labels we have? That is all the unique labels. So if you print trained, train is the original. Remember, this is the main data frame after reading the train.csv file. So if you do train.discourse_type.unique, you will get all the unique discourse types. And we have lead, position, evidence, claim, concluding statement, counterclaim, and rebuttal. And then similarly, I need to understand how many text document there are within the train folder. So for that, I just do train.id.unique. And then that many numbers are actually my different .text file that we have within the train folder. And we can see there are 15,594 train text. Next up, I'm going to convert the Kaggle train dataset into a NER token array that we can use to train an NER transformer. So you have already seen we have 7 discourse type or 7 classes, which are lead, position, evidence. So here I am creating B underscore lead, I underscore lead, B underscore position, I underscore position, this kind of thing for each of those 7 discourse types. So we will have total 14 arrays like this. Now, here's the fundamental that why do I need these B underscore and I underscore? And because these two things are used to indicate the boundary of a named entity. So in an NER, that is named entity recognition project, the prefix B underscore is used to indicate the beginning of a named entity and is typically followed by a label indicating the type of entity. For example, B underscore person for the first token in a person's name. The prefix I underscore is used to indicate tokens that are inside a named entity and is also followed by the entity type. For example, I underscore person for the second and subsequent tokens in a person's name. So in an NER, the goal is to identify and classify named entities such as people, organization, and locations in a text. To do this, NER models often assigns a label to each token in the input text, indicating whether the token is part of a named entity and if so, what type of entity it is. Now, in this particular project here, our entities are the 7 different discourse type, that is lead, position, evidence, claim, conclusion, counterclaim, and rebuttal. And so I am creating these beginning of lead and then inside lead, beginning of position, inside position, beginning of evidence, inside evidence, things like this. And also for a couple of other variables to be defined. Max length, which is I'm setting it at 1024, means that each token array will have a maximum length of 1024 tokens. Then initialize the tokenizer object with this line. And also I have to define 2 more variables, train tokens and train attention. So train tokens, initializing these with np.zeros, and the train tokens array is of shape length of unique doc list, unique doc IDs, and the max length. This array will store the tokenized versions of the text documents of train dataset. Similarly, train attention, this is also of the same shape, that is len of unique doc IDs and max len, and this array will store the attention mask for each tokenized document of train dataset. I further need to define these 4 more variables: train lengths, target B, which is just all the B position, beginning position for each of the 7 different classes or discourse type, and similarly targets I, which are all the I position, that is inside positions, that is I lead, I position, evidence I claim, I conclusion, I counterclaim, and I rebuttal. And then target to ID map. So this will map each of the discourse type to a particular number. And so after defining all these variables, I have to prepare my entire training data with a util function. So in the next line, I'm just doing that, prepare data, and I will come to this function in a second. Prepare data, and to that you pass all these arguments. Now, this prepared data is very important, and I have defined that within my util file. So let's go over it. Yeah, so that's my prepared data. So this will do, what this will do is prepare the data for the NER model by tokenizing the training text, encoding the tokens, and generating the targets. And it takes quite a few arguments. And finally, okay, so let's just go step by step with this function. All right, the first line is in this prepared data method is this assert statement. I'm checking that np.sum of train group by IDs, that is grouping by all the IDs, and take only the values of the discourse start column, and .diff should be less or equal to 0. And if you sum all of them, this entire sum should be exactly equal to 0. So what I'm doing is here that first, what is discourse start? So if I go back to my train.csv file, discourse start, this is the column. I have one discourse start and one discourse end. So discourse start is the character position where the discourse element begins in the essay response. And with this particular assert statement, I am checking whether the difference between consecutive discourse start values for each ID group in the train data frame is strictly greater than 0. That is, the discourse start values are in ascending order for each ID group. So here actually this discourse start.diff method of pandas calculates the difference between consecutive discourse start values for each group. This returns a new series with the same length as the original series, where the first value is nan, that is not a number since there is no previous value to calculate the difference with. And this expression of checking whether it's less or equal to 0 checks whether each value in the series is less than or equal to 0, which should be false because I'm assuming the discourse start values are in ascending order, and hence next value minus previous value should be a positive number because it's ascending series. That is, I'm going row by row. And np.sum, this sums the boolean values in the series. The boolean values, because .diff less or equal to 0, this expression will give me a boolean value, right? So the false equal to 0, true equal to 1. So the assertion statement, that is this entire statement equal to 0, raises an error if the sum is not equal to 0. That is, if there is at least one group where the discourse start value are not in the ascending order. And the reason for this check is that the function processes each document sequentially and assumes that the input data is sorted. If some discourse start values are not sorted in ascending order, it would mean that the training data is not properly ordered by the start position of the discourse in the text. This could potentially cause issues when iterating through the offsets of the tokenized text and aligning them with the target discourse spans. Specifically, if the discourse span in the training data are not in ascending order, it may be possible to miss or incorrectly map some of the target spans to the tokenized text. And hence, the very first statement I'm checking is this assertion check that all the values of the discourse start are in ascending order indeed. After the assertion check, now I'm going to start looping through each of the train text files within this loop. So I'm just looping over the entire length of unique doc IDs. And after crossing each 100 text, I'm just printing the ID number. All right, so the next here, I'm just opening the text file, read the content, tokenize the text using tokenizer, and save the tokenized input and attention mask in train tokens and train attention arrays, respectively. It also saves the length of the original text in the train len array. Yeah, so this is just simple code. I'm just reading it with this open and then passing the file. And here with the tokenizer.encode plus, I'm just tokenizing each of the text. And then after tokenizing, I will have access to this tokens variable, which will have input IDs and also attention mask, which I am saving in two arrays, train tokens and train attention. And in the tokenization part of the block, we can see that return offset mapping I have set to true. So what exactly does this do? So when return offset mapping equal to true, the offset mapping for each token in the input text are returned in the output dictionary. So offset mapping is a mapping between the original text and the tokenized text, where each element in the mapping is a tuple, which is a tuple of start offset and end offset that corresponds to the token in the tokenized text. So start offset is the starting position of the original text corresponding to the token, and end offset is the ending position of the original text corresponding to the token. By default, return offset mapping is set to false, which means that the offset mapping is not returned. Hence, because here in this exercise, I need those offset mapping, hence I set it to true. So let's take a quick example. I have a sentence, the quick brown fox jumps over the lazy dog. When we tokenize this sentence using a tokenizer, such as the tokenizer class from the transformer library, we get this following tokenized output here. It's a list, and each of these are actually tokens. And each token corresponds to one or more characters in the original sentence. The return offset mapping equal to true parameter in the encode plus function tells the tokenizer to return a list of offset mapping, where each mapping indicates the character positions in the original sentence that correspond to a particular token. For example, the offset mapping for the token quick might be 4-9, that is this particular word, indicating that the characters at position 4, 5, 6, 7, and 8 in the original sentence correspond to the quick token. And here's an example of how the offset mapping might look for the entire sentence. And that's your offset mapping. So here for the token D, 0 is the starting position, 3 is the ending position. For the token quick, 4 is the starting position, 9 is the ending position. So that's what you will get when you set your return offset mapping equal to true. And this information can be useful in various natural language processing tasks, such as named entity recognition or parts of speech tagging. And so back in our prepared data method in utils.py file, so we have set the return offset mapping equal to true. And then with this line right here, I am grabbing that offset mapping. So you get your tokens and you just extract the offset with tokens and then pass offset mapping. This is the key. And then we define a data frame here with this condition train.id equal to current doc id num. And then we will loop over these data frame with this little loop over here using iter rows. And then grab hold of the discourse start and discourse end. Remember, these are two numbers we have with each row. So I'm defining them to be disk start and disk end. And then in the next line right here, offset index more than len offsets -1. If this is the case, then we will break out of the loop. So here what I'm very much doing is it checks whether the current offset index is within the bounds of the offset array. If the index is out of bounds, we will break out of the loop. And if that is not the case, then we'll proceed with defining more variables, token start, token end. This will just be the two elements of the offset index. Remember these offset index, that will give you a single tuple, that is two element of the tuple, and token start, token end. That's what we just saw right here, that each of these tuple represent token start, token end, token start, token end. And that's what I'm grabbing here. And then defining these Boolean variable beginning equal to true and run another loop with these while condition. All right, but before proceeding with the description of the while loop and how it's working, I just want to revisit a quick point that the whole purpose of these prepare data method is to build two tensor or two arrays, which are these targets B and targets I. And if we recollect, these two arrays were defined in the original in the final notebook right here. So we had I'm just revisiting few things that we discussed earlier, that we have all these 14 classes of named entities, that is B lead, I lead, B position, I position, etc. And then we define two arrays containing the targets. B contains all the B position, all the beginning named entities, and targets I contain all the intermediate named entities. So these targets B and target I arrays are used to store the ground truth labels for the beginning and intermediate tokens of each named entity class in the tokenized input. Each class has its own pair of arrays, that is, each is starting with B and then I, B and then I. And these targets B and targets I have the same shape as my train tokens and train attention. So basically they align with the tokenized input and attention mask. So by having the same shape as train tokens and train attention arrays, the targets B and targets I arrays ensure that the ground truth labels are aligned with the tokenized input and attention mask. This alignment is essential for training the model, as it helps a model learn to map the tokenized input to the correct named entity labels. All right, so with that background, we'll go back to our prepare data method again. So here in this method, we are building those targets B and targets I arrays and preparing these two arrays to be fed finally to the training model. So that's the whole purpose of these prepare data method. Okay, I just want to put the whole purpose of this method right in the beginning in this part. So prepare data, it is used to convert raw text data into a format suitable for feeding into the NER model. The primary purpose of this function is to tokenize the input text, create attention mask, and generate target labels for the beginning and intermediate tokens of each named entity. And to achieve that, this method updates two arrays, targets B and targets I. Yeah, so that's precisely exactly what is the purpose of prepare data. So coming back to this particular part here, till which we already discussed. So the beginning, we define this Boolean variable true, set it to true, to track whether the current target is a beginning of a span or not. And then this while loop checks whether a discourse end is more than token start. So this entire while loop continues as long as the discourse end position, disk end, is greater than the token start offset position, that is token start. For example, let's take an example. So here, for example, consider a target span in the input text with a start position of 4 and an end position of 7. If the offset mapping of the tokenized input text is like this, that is, say 0, 0, 0, 2, 3, 5, 6, 8, 9, 10, in this case, the while loop would iterate through the tokens with offset position of 3, 5 and 6, 8, since they fall within the boundaries of the target span. The final token 9, 8 will be skipped since it falls outside the target span. And then the next super important conditional check is this line right here. That is, if token start is more than disk start and disk end is more or equal to token end. So this line is a conditional statement that checks whether a token lies within the span of a named entity or discourse element in the text. It is used to determine if the token should be assigned a label as part of the named entity. Let's go through an example to understand it properly. So this is my condition: if token start more or equal to disk start and disk end more or equal to token end. And these are the variables actually mean. Token start is the start position of the current token in the text. Token end is the end position of the current token in the text. Disk start, this is the start position of a discourse element that is named entity in the text. And disk end is the end position of the discourse element or named entity in the text. So the condition token start more or equal to disk start and disk end more or equal to token end checks if the current token lies within the boundaries of the discourse element. And for the example, consider this line. This is an example text with a named entity in it. Note this part, named entity within 2 square bracket. So here the disk start, that is this variable, is the position of the opening square bracket, and disk end is a position of the closing square bracket. Now let's consider the tokens named and text. So we will be checking these two tokens. One is named and one is text. Whether and what we'll be checking for? We'll be checking if they should be assigned a named entity to them. So for the token named, token start position will be the position of the letter N in named, and token end position will be the position of the letter D in named. Since token start is within the named entity, disk end is greater than or equal to token end, the condition that token start greater or equal to disk start and disk end greater or equal to token end is satisfied. Therefore, the token named is part of the named entity. And similarly, check for the another token, which is text. In this case, the token start is the position of the letter T in the first text, and token end is a position of the letter T again in the first text. And obviously in this case the token start is less than disk start, so the condition token start is more or equal to disk start and disk end is more or equal to token end is not satisfied in this case. Therefore the token text is not part of the named entity. So coming back to the code in the method, this conditional statement is pretty much used to determine if a token should be assigned a label in targets B or targets I arrays as part of the named entity. And then I define this k variable which is equal to target ID map, and then to that I pass row.discourse type. So our discourse type is one of those 7 classes of named entity. And what is target ID map? That's a dictionary that we have defined in the notebook right here towards the top. So we have 7 different discourse type, and each is assigned a particular key, which is a number from 0 up to 7. So that's my target ID map. And here what I'm doing is if beginning. So beginning again is a Boolean variable that has been initialized to true. If beginning, then target B k ID number offset index equal to 1, and then set beginning equal to false. Now this is pretty important, so let's understand what exactly this is doing. But first of all, here target B is a list of numpy arrays where each array corresponds to the beginning target labels of a specific named entity class. This variable k has been defined here, and it is just the index of the named entity class in the targets B list. And ID number, this is the index of the current document in the unique doc IDs list. This helps to locate the correct document in the targets B array. And offset index, this particular variable, we have defined it right here, offset index 0. And then if offset index, we have included a break statement here. That is, if offset index is beyond the length of offsets, then we break the whole for loop here. So offset index is the index of the token in the tokenized input for which the label is being assigned. So with this line, that is targets B k ID number offset index equal to 1. With this line, you mark the token at the beginning of offset index as the beginning of a named entity of the class k. This assignment is crucial for training the NER model, as it helps the model learn to recognize the start of a named entity in the text. All other tokens in the array that are not part of the named entity or not the beginning of the named entity will have a default value of 0, indicating that they should not be considered as the start of a named entity of the class K. So after this assignment is done, I am setting beginning to false, because the first token of the discourse span has already been processed as the beginnings. That means the next will be not a beginning, and that's why I'm setting to false. And the else statement is obvious, that if beginning, that is if this is not a token, is not a beginning token, then I should do the same assignment to targets I array, because targets I array will hold all the inside token. And after these if else statement is over, you run this two line, offset index plus equal to 1, and if offset index is more than len of offsets minus 1, then break. So basically in these two lines, what's happening is that after updating the target arrays, we increment the offset index variables to move to the next token in the input text and update the values of token start and token end accordingly. This process continues until we have processed all the tokens in the input text or have reached the end position, that is disk end or discourse end of the current target span. And so that's my prepared data, and in the main notebook you execute that prepared data in this cell right here and pass all the arguments, that is train, unique doc IDs, train lanes, tokenizer, train tokens, train attention, root D, max lane, target ID map, targets B, and target I. And remember, we have already defined all these variables before this cell. And then I just want to run a quick histogram on the length of the training dataset. So I use this train length, this variable, and remember this train length is a variable that was initialized to an empty array in the notebook right here. But then this train length will get updated inside the prepared data method. Let's see how it is getting updated. Yeah. So train length dot append len text dot split. So that's how train length will give me, when I run a histogram on this train length, that will give me an understanding of the word count in my training data set, so that I can see that what's the max len we can reasonably use in this case. So when I do this histogram, I run this histogram code right here. I just pass the train length with the bins of 100. And this is a histogram of train word counts. All right. And on the horizontal axis, that's what we have, train word count. We can see that it's kind of ending at 1200, but after like 1050 or 1100, the occurrences are very rare. So what this tells me is that from this histogram of train word counts above, we see that using a transformer width of 1024 is good enough for capturing most of the data signal and also not having too large of a model. And next, I'm going to build a tensor with interleaving structure to represent 15 classes of targets. And this is a simple couple of lines of code to do that. But here, there's a very important concept to understand, and I will go over it in a second. So first, see what I'm doing here. First, in this line, targets equal to np.zeros, len, unique doc IDs, max len, and 15. So I'm pretty much creating a 3D NumPy array. Why 3D? Because I have this first dimension, second dimension as max len, and the third dimension as 15. And data type is int32. The purpose of this array is to store target labels for each unique document and for each token, that is word or character, up to the maximum length defined by this max len variable, and the depth 15, that is this third variable, third dimension. This depth 15 layer is used to store different label information for each token. And then I run a loop for k in range 7, and then update these targets 3-dimensional NumPy array with these two lines. So we will go over these lines step by step, but let's see what this loop does. So in this loop, for each class, that is I have 7 classes of lead, position, evidence, claim, conclusion, counterclaim, and rebuttal, which are all the discourse types. So I run the loop through these 7 classes, and the code assigns the corresponding beginning targets B and inside, that is targets I labels, to the targets, that is this variable, which is a 3D NumPy array, in an interleaved fashion. So for each class, it assigns the beginning labels to the even indices determined by this expression 2 times k, and the inside labels to the odd indices determined by 2 times k plus 1 right here. The result is an interleaved structure that allows for efficient storage and retrieval of target labels for each component or each entity type during the training and evaluation of the NLP model. So the targets array here, targets array will store the beginning label for class K at depth 2 times K, and the inside label for class K at depth 2 times K plus 1. That's how it will continue working. So the for loop iterates 7 times and sets the values of the even numbered columns, that is 0, 2, 4, etc., to the values of the targets for the beginning of entities, that is targets B for each entity type, and it sets the values of the odd numbered columns, that is 1, 3, 5, etc., to the values of the targets for the inside entities, that is targets I for each entity type. And finally, I do this line, targets from the first dimension everything, second dimension everything, and third dimension I, that is the last dimension 14th, I set it as equal to 1 minus np.max, targets axis equal to -1. Let's understand what it's doing. Basically, it just sets the values of the last column to 1 minus the maximum value of the targets in the third dimension. So this column corresponds to the outside of an entities in the text, meaning it is not part of any entity. This is done to ensure that the model can distinguish between entities and non-entities in the text. And here in this expression np.max targets x is equal to -1, this calculates the maximum value along the last axis. This x is equal to -1 notation is shorthand for selecting the last axis. And after doing these operations on the targets variable and building the targets tensor in this interleaved fashion, if you just print the targets, you will get this structure. So this is my targets variable. It's a 3-dimensional array or tensor, and just as we were expecting it, because we built it to be 3D NumPy array. And each of these internal values are set according to these calculations that we have performed here. And all right, so now the question is that why exactly the targets array is built like this with even and odd positioning of target labels. So interleaving structure for target labels like the one we used here are quite common in deep learning NLP projects, particularly for sequence labeling tasks and especially when handling a multi-class problems with multiple entity types, which is the case here. The structure has a couple of benefits for NLP NER model training and evaluation. First, a compact representation. So by interleaving the beginning and inside labels, the targets array effectively stores information about the named entities in a compact manner. This allows the model to have a single array to reference when it needs information about the labels, simplifying the process of accessing and updating the target labels during training and evaluation. And then the next one is easier indexing. So the even and odd positioning makes it easy to index and retrieve the beginning and inside labels for a specific argument component. You can directly access the beginning label for the kth component or kth entity type using the index 2 times k expression and the inside label using the index 2 times k plus 1. this clear mathematical relationship between the component index, that is the entity type index, and the target label position simplifies the process of working with target labels during model training and evaluation. And the third benefit of this interleaving structure is flexibility. The interleaved structure allows for the possibility of extending the model to support additional types of labels or components in the future. You can add new components by simply extending the depth of the target array and updating the indices accordingly. And if you take a look at the target's variable structure after this interleaved structure, this is the form it will take. It's a three-dimensional NumPy array. And here we can see that each innermost array has 15 elements and the 15 columns actually. So the 15 columns in each innermost array represent the interleaved beginning and inside labels for the 7 classes or entity types, as well as an additional column for tokens with no labels, that is the last 15th one. Alright, and after this, our prepared data is done, so we can actually build the model. And for building the model, we will run these simple 2 lines with strategy.scope, model equal to build model. And to this build model method, you pass the model name and max length. Now, this build model is another util method that we have defined in train.py file. We will come to that in a second. So yeah, and here we will use a Longformer backbone and add our own named entity recognition head using one hidden layer of size 256 and one final layer with softmax. And we will use 15 classes because we have a B class, that is beginning class, and I class for inside class for each of the 7 labels. And we have an additional class called 0 class for tokens that do not belong to one of the 14 classes. So now let's understand this build model method. I think I have defined it here in train.py. Yes, that's my build model. And the build model method is actually quite simple. I have defined the tokens and attention with tf.characters.layers.input. And to this input, you pass the shape, name, and dtype. And then in this line, you load the configuration file from the pre-trained model, and then tf_automodel.from pre-trained. That's where you load your model instance. And then output from these base model instance is when you pass tokens and attention mask to the base model instance. That's what is your output, which is X in this case. Now note, this output X, I will have 2 things. I will have an X0 and I will also have an X1. Now X0 is the final hidden activations, also called last hidden state, and has shape of batch size, token sequence width by number of Longformer features. Actually, let me put that thing here. So what I'm meaning is these X0 is of shape these, that is batch size, token sequence width, the number of Longformer features. All right. And X1, if you do X1, that would be your Pooler output. And since we just ignored the Pooler output, we do not apply loss to the Pooler output layer, and they don't have gradients. And reason for not using the Pooler output is because we need features for each token. The Pooler output will only give us features for the entire sentence. So we go ahead with the X0, and then in the next line, I'm just adding a dense layer with 256 units and a ReLU activation function to the model. And after that, in this line, add a final dense layer with 15 units and a softmax activation function, which outputs the probabilities of each of the 15 entity types for each token in the input sequence. So here I have 15 because I have 15 classes or 15 entity types. And with that, finally, I have this X as the output from those final dense layer. So then my model will just become tf.keras.model. You pass your inputs and tokens and attention. Outputs is your X because that's my outputs. And finally, model.compile. And for the optimizer, I'm using Adam and categorical cross entropy for loss, and metrics, again, categorical accuracy, and return this model. So this is my entire build model workflow. And then this build model is what I am using in my notebook here after doing the data preparation. Let me see. Yeah, that's the line. And the next steps are just the regular workflow for training your model. You define the learning rates. So this is a range of learning rates I have defined. And then the learning function, which will be passed with this learning rate scheduler. So after you define this learning function, then tf.keras.callbacks learning rate scheduler, and you pass the scheduling function, which is this learning func, and verbose is true. All right, now, so train valid split of 90% and 10%. And for that, I just need a set of train index and valid index. So I'm taking 90% of the data to be my train index, and the rest are valid index. And I'm doing that with np.random.choice. Then you to the choice you pass np.arange, entire length of the unique doc IDs. And then you pass the second argument as 0.9, that is 90% of the unique doc IDs. And so that will give me a choice that will randomly choose 90% of the data. And then for the valid indexes, I am making use of this np.setDiff ID. So this setDiff1D returns an array of indices that are not present in the train IDX array. So this method takes two arguments. The first one is np.arange and the entire length of the unique doc IDs. And the second argument is train IDX. That means the indices which have already been taken. So the valid index, this IDX, this variable will give me the rest of the IDs which are not in train IDX array. And that's it. Then you can do model.fit, that is train the model actually. And here you pass to the X, you pass the train tokens with the train indexes and also the train attention. For Y, that will be my train IDX. And then also you need to pass the validation data, which will be my train tokens and valid indexes. Similarly, train attention and valid indexes. Callback is error callback, epoch. These are all constant, batch size and epoch. And after the training, I am also saving the model with this model.saveweights. And after that, the validation part. So here is the inference for OOF, or out of fold segment. So we will now make predictions on the validation text. Our model makes label predictions for each token. We need to convert these into a list of word indices for each label. Note that the tokens and words are not the same. A single word may be broken into multiple tokens actually. Therefore, we need to first create a map to change token indices to word indices. And hence for that purpose, we define this variable target ID map updated. It's a dictionary with all the 7 classes and also a blank class. So these, we remember these are all our discourse type, lead, position, evidence, claim, etc. And we just assign to each of these discourse type a number as a key value. And target ID map is the variable that we will use in the very next step for our prediction or inference. And for this, I'm going to use this another method, calculate preds, which we will define in the train.py file, and I will come to that in a second. So calculate preds is a function that will be a long function which will be used for inference. So let's go to train.py and let's check out this calculate pred function and how it works. All right, this function takes quite a few arguments. A tokenizer, which is a tokenizer object used to tokenize the input text. Target ID map updated. This one is a dictionary. We saw it here. This dictionary where we have a key value for each of the class. And max length is a maximum length of tokenized input sequence. Root D text IDs. This is a list of IDs corresponding to the input text files. Preds. This is a NumPy array of predicted labels for each token in the input text files. Dataset, a string indicating whether the input text files are from the training or test set, and the default is string. Verbose, it is just a boolean indicating whether to print progress updates during function execution. And returning, this whole function will return you a pandas data frame containing word label predictions for each input text file. The data frame has 3 columns: ID, which is the ID of the input text file; class, which is a predicted label for the word; and prediction string. This is a space separated list of the token positions that make up the word. And so initially just I'm declaring these variable all prediction and empty list, and then start the looping over the entire length of preds. And file ID number equal to text ID's ID number. So here I am retrieving the ID of the current input text file based on its index in the text IDs list. So so note here that these text IDs, this particular list is actually my unique document IDs for the valid indexes that we have defined in the notebook. And to get the tokens, I'm using these tokenizer and encode plus method from Hugging Face transformer, and that will give me the tokens. And then from that tokens, I am getting the offset mapping by grabbing the offset mapping key from the token. So this tokens variable will have a lot of keys, and you can see them when you print it out. In this line, I'm only taking the offset mapping from those keys. And just to understand these offset mapping, so in NLP, text is tokenized, meaning that it is split into individual words or subwords. The tokenizer.encode plus, this method is used to tokenize the input text and obtain a dictionary of various properties, including offset mapping. And offset mapping is a list of tuples we already discussed earlier in this video, where each tuple represents the start and end character positions of the corresponding token in the original text. For example, if the token cat, C-A-T, appears in the text, which is, say, the cat sat on the mat, the offset mapping for the token would be 4, 7. That is, 4 is the starting position of the cat token, and 7 would be the ending position of the cat token. And similarly, it goes for each token for the entire text. And in this method, calculate pred, the offset mapping is used to map the positions of the tokens to the positions of the words in the original text. This is done by iterating through offset mapping and keeping track of the positions of the spaces and delimiters in the original text. So that's what I'm doing in these lines. So in this line, so what I'm doing is I'm looping through the text, the entire text file. And what is my text file? We have already defined the text file to be the current.txt file that I'm reading it here. And then I'm looping through the entire range of the len text and run an if-else statement with which checks some delimiters and spaces. So let's look at this if statement here. So the if condition here first check if the current character is not a space, that is this one, is not a space or any of the other delimiters specified by this one and this one and this one. So and also blank is true. This blank boolean variable is true. In that case, if all these conditions are satisfied, in that case, I am appending that text, that portion, to this W array. So basically, if this condition is met, all these conditions are met, then the code appends the index of the character I to the list W and sets blank equal to false to indicate that the current character is not a space. And then the else condition here, that is if the current character is a space indeed or any of the other delimiters specified, the code sets blank to true. This is done to ensure that each word in the text is only recorded once, even if there are multiple spaces between the words. When blank is true, the code does not append the index of the current character to W. And once again, here we are doing the inferencing part with these codes, and all these regex checking and getting the actual words is happening on the valid set, that is from the valid set of text files. And just want to remind here that to keep things in perspective, that this calculate preds, this method is only for inferencing, and the invocation of that method in our main notebook is in here in this cell, where we are calculating out of folds by invoking or executing this calculate preds method that we are currently describing. And so in the calculate preds method, these preds argument on which we are running this entire loop right here, that is for id number in range lane of preds, this is coming after I do the model.predict. So I think, I'm not sure if we have discussed this particular cell before. So let's go through it quickly so that our everything will remain in context. So this preds variable, preds argument, is coming after running my model, after doing the prediction from the model. So I do model.predict, and model has already been, we have already got the model by doing the entire training with model.fit. So after the training, after the fitting is completely done, here I am just doing the inferencing, and when I run model.predict, I get this P, and that P is the prediction or inferencing. So this P is the prediction array, which has a shape of number of samples by sequence length by number of classes. So something like this. So if I run these P.shape here, it will print something like whatever was a number of individual sample, probably 14,000 something. So this is the shape of this P, that is number of samples, sequence length, which is 1024, and number of classes, which is 15. And then I use these prediction from the model.predict and pass it as an argument to my calculate prediction, and that's how I get this out of fold data frame. So this preds argument that my calculate prediction function takes, that is actually these OOF preds or out of fold preds. And how do I get this out of fold preds? With this line, that is, I run np.argmax on my P, which is my predicted array, and on the axis of -1. So basically that means that in this code, this np.argmax will find the index position of the maximum value along the specified axis in an array. In this case, the prediction array is P, and the maximum value corresponds to the highest probability of a token belonging to a certain class. For example, entity type. In this case, that could be position, that could be lead, that could be conclusion. And P is the prediction array. And each element of P, that is Pijk, represents a probability that the token at position J in the input sequence I belongs to class K. And x is equal to -1 by this line, we are looking for the maximum value along the last axis, which corresponds to the class probabilities. This means that we are finding the class with the highest probability for each token in every input sequence. So the whole line OOF preds equal to np.argmax P x is equal to -1 results in an array with the shape of number of samples by sequence length. That is, the first dimension will be the number of samples, and the second dimension will be sequence length, where each element in the sense, if I do OOF preds ij here, this is the index of the most likely class for the token at position j in the input sequence I. So OOF I preds, this particular variable, will be used in the project to evaluate the model's performance by comparing its predictions with the ground truth labels. So that's a whole background or context of doing this particular method, calculate preds, because calculate preds will take these OOF preds as its prediction array. All right, now come back to our function. Where were we? Yeah, we described up to this. So here I was updating these W array based on this regex check, that is which token should be added to W or not. And here again, this W array stores the starting position of each word in the text. And so here, after this if else block is done, I am adding to W a very large number to ensure that any tokens beyond the end of the text are mapped to the last word in the text. All right, and so after that, I initialize this new variable word map here. So this word map is a list of indices where each index represents the position of a word in the original text. The multiplication of -1 here, that is, I'm initializing word map with the whole these np.1s, and the shape is max len, the type is int32, and multiplying the whole array with -1, because this multiplication of -1 is used to initialize all elements of the word map to -1. And this is because in subsequent loop, that is here in this loop, the index word map I'm setting it to w underscore I. Now, the -1 initialization indicates that initially, that is before this assignment, none of the tokens have been assigned a word index. And that is the whole reason of initializing the entire array with -1. All right, now take a close look at this block of code. So word map here in this variable is used to map the position of the tokens to the position of the words. And these W array that we have here, this W array stores the starting position of each word in the text. Thus, WI, that is this variable that we have initialized with a 0 here, and then we are using within this block, this WI represents the index of the word in the W array that the current token belongs to. And here in this block, specifically this line right here, we are iterating over each offset pair in the offset list. Each offset pair represents a start and end position in the input text for a particular word. So let's take an example to understand this block of code better. Okay, so this is the block of code I'm referring to, and let's say that this is the offset list we have. It's a tuple of starting and ending position. So each tuple represents one starting position, one ending position. And then this is our W list. So initially WI is set to 0 and word map is an array of -1 values. We then loop through each offset and set the corresponding word map value to the appropriate index in W. So in this line right here, while offset I0 is more or equal to WI plus 1, we are checking that if the start position of the current offset pair, which is offset I0, is greater than or equal to the end position of the current word in the W list, which is W and then WI plus 1. For example, let's consider the first offset pair in the offset list, which is 04. That is, I'm referring to this offset list right here, and the first pair is 04. So this offset pair represents the start and end position in the input text for the first word in the W list, which is 0 to 4. When I is 0, the condition offset I0 greater or equal to WI plus 1 is equivalent to 0 greater or equal to 4. Since this condition is false, we do not enter the while loop at all. Similarly, when I is 1, that is the next iteration or looping value of I have this condition referring to whether 4, that is this number, is greater or equal to 8. Again, since this condition is also false, we do not enter the while loop. And then for I equal to 2, I mean, just exactly in a similar fashion, this line right here will mean whether 8 is more or equal to 13. And since this condition is also false, we do not enter the while loop. So when this entire code block is executed, the final word map will be something like this. A list of values where some of them are set at -1, that is, they were the initialized value. And once again, this word map, what it represents is that it's a list of indices where each index represents the position of a word in the original text. Because what basically we are doing here with this block is map the positions of the tokens to the positions of the words. And then this line pred equal to preds, then ID number, comma, and dividing the whole array by 2. So this notation of comma is used to access all the elements in the row with index ID number of a two-dimensional NumPy array preds. The comma in this particular expression is used to separate the row index ID number from the column index, which is left blank, indicating that we want to select all the columns in the specified row. The resulting one-dimensional NumPy array pred contains the model's prediction probabilities for all the output classes for the sample represented by ID number. And we are dividing by 2 because this can be useful in some cases, such as when models' predictions are too confident and need to be scaled down, or when the prediction probabilities need to be adjusted to balance the model's accuracy and recall. All right, let's move ahead. So this while loop right here, starting with I equal to 0, is used to iterate through each token predictions in the pred array, where each element in pred corresponds to the predicted class probabilities for a single token in the input text. And I start with start equal to pred I, and then with an if start is 0, 1, 2, 3, 4, 5, 6, 7. So this if condition is checking if the predicted starting index start is one of the 8 values of 0, 1, 2, 3, 4, 5, 6, 7 coming from our different classes. Remember, we had 8 different classes, which was defined with this dictionary right here: lead, position, evidence, claim, etc., etc. So these values of 0, 1, 2, 3, 4, 5, 6, 7 represent or correspond to the 8 possible labels for the starting index of a word in the given dataset. So if the starting index starts has a value in this list, it means that the model has predicted that the current token is the starting token of a word. And in that case, I add that word map I to my prediction array. All right, and then increment I plus equal to 1. And then this if condition, if I is more than max length, I'm breaking out of this loop completely, because this if condition checks if the I has exceeded the maximum length of the input text max length. If exceeded, it means that we have processed all the characters in the input text and we need to exit the loop to avoid any index out of bounds errors. So this while loop, starting with I equal to 0, is used to iterate through all the token predictions. Inside the loop, the code checks whether the current token corresponds to the start of a new word. If it does, then the code extracts the corresponding word level prediction by looking for all tokens with the same class prediction, that is pred I, and appending their corresponding word indices in word map to a list called prediction, that is this line right here. Now I will come back to this particular line, that why I'm adding 0.5 here in a second. But before that, let's go to the else statement. So the if statement was if start is in one of these numbers. So if that is not the case, that is if the starting index start is not in this list of 0, 1, 2, 3, 4, 5, 6, 7, it means that the model has predicted that the current token is either a continuation of the previous word or is not a part of any word. In this case, the code simply skips the next token without appending any prediction. And that's taken care of by this else block right here. That is here, I'm not doing anything. I'm only incrementing the I value and going to the loop again. Now about this particular line, that is while I'm checking, while pred I is equal to start plus 0.5. So it checks if the next character in the prediction array is a continuation of the current token. The pred array, that is this particular pred array, contains a model's predictions for each character in the input text, and each prediction is a floating point value between 0 and 1 that represents the probability the character belongs to one of the 8 possible level, that is 0, 1, 2, 3, 4, 5, 6, 7. And if the value of pred I is equal to start plus 0.5, it means that the current token has not ended and the next character belongs to the same token. And here these start variable is the label assigned to the first character of the current token. In other words, the start variable is the predicted label for the current character, which belongs to one of the 8 possible classes or labels, that is 0, 1, 2, 3, 4, 5, 6, 7. So therefore, if pred I, that is I'm talking about here, this pred I. So if the pred I is equal to the start plus 0.5, that is this value, it means that the model has predicted the continuation of the current token. Inside the while loop, that is a whole block here, the code appends a word index to the current token to the prediction list. If it has not already been added, then it increments the index I to move to the next character in the input text. And this process continues as long as the next character in the prediction array belongs to the current token. The while loop exits when the next character in the prediction array does not belong to the current token or the index I exceeds the maximum length of the input text. Now let's take an example. Let's say the model predicts the labels for the tokens or characters in a given text as follows. So these are my predicted labels: 0, 0, 0.5, 1, 1.5, 1.5, 2, etc. So here the character at position 2, that is this one, has a predicted label of 0.5, indicating that it is the continuation of the first word. Similarly, the character at position 4, that is this one, has a predicted label of 1.5, indicating that it is the continuation of the second word. So to summarize of this particular line of adding start plus 0.5 to check under this while loop, so here the start represents a predicted label for the current token scaled down by a factor of 2. The purpose of adding 0.5 to start is to check whether the next token in the sequence has a label that corresponds to the continuation of the same target class as the current token. For example, if the original labels in the preds array were integers, for example, let's say 0, 1, 2, 3, after dividing by 2, because we are scaling down by 2 right here, after dividing by 2, that is original array is 0, 1, 2, 3, and you divide each element by 2, you would get values of 0.0, 0.5, 1, and 1.5 respectively. So in this case, if the current token has a label of 0, adding 0.5 to it will result in 0.5. The while loop will continue in that case, and while loop indeed will continue as long as the next token has a label of 0.5, indicating that the next token is a continuation of the same target class. So this approach is particularly useful when dealing with multi-token entities, for example, named entities in NLP projects. By checking for this particular thing, that is pred I equal to start plus 0.5, the code ensures that it gathers all consecutive tokens belonging to the same entity before moving on to the next entity or non-entity token. And then after this block is completely executed, that is this while loop, I am creating a list, a prediction list from my original prediction array. So this original prediction array, like we remember that some of them will be -1 as it was initialized. And hence with this line, that is this Python list comprehension line, I'm creating a new list which only contains elements from the original prediction list that are not equal to -1, and -1 here represents that a word or token is not part of any named entity. So by filtering out those -1 labels, the new prediction list will only contain the labels or indices corresponding to actual named entities in the text. And finally, if a lane of prediction is more than 4, then I'm updating the all prediction tensor by appending file ID number and target ID map updated with the start. So the reason that I am using these if condition here is that the prediction variable contains a word level prediction for a given token in the input text. So if the length of the prediction is less than 4, it means that the token does not have enough context to make a confident prediction about its entity level. And hence this condition that length of prediction should be more than 4, and only then I'm appending the rest of the things to all predictions. So once again, with this if condition right here, that is length of prediction should be more than 4. So this ensures that the only predictions with sufficient context are stored in the all predictions variable. This can help avoid incorrect or unreliable predictions that may be made based on incomplete information. And then the final 2 lines is just creating the data frame by defining this variable df inference. And the data frame is created from this all predictions array, which is a NumPy array. And this all prediction, when we are appending, we are appending file ID number. Then I'm appending the class, which is taken from this target ID map updated dictionary. And also the prediction string that I'm doing with this join statement. So an empty string join, and then a list comprehension strx for x in prediction, right? So I have actually ID, class, and prediction string, and that's exactly the column names that I'm defining here, dfinference.columns. And that's a data frame I'm returning from this entire function. This is a long function. So calculate preds. So that's the final return object from this function, return df inference. And based on these df inference, I will proceed with the evaluation on this competition. And so when you execute the calculate preds function finally for the inference in the notebook, I get the out of fold data frame, and I print out of fold data frame, and that's the result. So I have all the ID, class, and prediction string. And after getting the out of fold data frame, I need to do the validation metric, and that's what I'm going to do now. But before that, I need to also define a metric compute method as required by the competition evaluation metric. But first, I just need a list of valid IDs, and so I apply this line here with train.loc to get all my valid IDs. And basically, this line of code is selecting a subset of rows from the train data frame based on a condition. Specifically, it is selecting the rows where the value in the ID column is present in a list of unique document IDs that are part of the validation set. And this is my validation set, as we have selected early while folding our entire data set in 9:1 ratio. Valid IDX is that validation set. So let's quickly revisit the evaluation metric for this competition. So that's the official page, and it says for each sample, all ground truths or predictions for a given class are compared if the overall overlap between the ground truth and prediction is more than 0.5, and the overlap between the prediction and ground truth is more or equal to 0.5. The prediction is a match and considered a true positive. If multiple matches exist, the match with the highest pair of overlap is taken. Any unmatched ground truth are false negatives, and any unmatched predictions are false positive. All right, so we in the initial part of the video, early part of this video, I have already discussed in more detail the meaning and interpretation of these 3 points. So you can just check it out again, just in case if you have not watched that part. But anyway, let's now go ahead and put these in methods so that we can do these calculations on our inference data. All right, so first I define a overlap percentage method that's in my util file. And it's a rather easy function, calculates the overlap between predictions and ground truth, and overlap percentage used for determining true positives. In both the overlap, the numerator is the size of the intersection, and both calculations have to be at least 0.5 for the prediction to be considered a hit. Now, first is set predictions. That is, I'm just applying set method on row.prediction string pred. And remember, the row is the argument to the method, and it is expected that this row will have a an attribute of prediction string pred, so that I am splitting based on that. And also that's my prediction, and then ground truth. Just similarly apply set on row.prediction string ground truth, and then take the length of both of them, and the intersection will just be len set gt intersection set pred. Simple, right? And the overlap 1 is just divide the intersection by len gt. That's your overlap 1, and overlap 2 is intersection divided by len pred. All right, so that's my overlap percentage method, and then this is the main method, compute macro F1 score. So that is where I will apply the Kaggle's own competition's official evaluation metric here. And so yeah, let's go through this method. And one thing I forgot to mention, these intersections. So here, this intersection method is used to find the common elements between the two sets, that is the overlap between prediction string pred and prediction string gt. So that's the whole purpose of this intersection. And now coming to our compute macro F1 score. So first extract these two lines. What you see here, what I'm doing is extracting the relevant columns from the predicted and ground truth data frames and create copies of these data frames to avoid modifying the original data. So the relevant columns are ID, discourse type, and prediction string, and then I'm applying reset index and then copy. So yep, and here I'm passing reset index drop equal to true for both of them. So this will what this will do is the old index is dropped and a new sequential index is created. And in the next two lines, that is these two lines here, this is adding a unique identifier for each prediction and ground truth by adding a new column called pred ID and GT ID respectively. And in the next section here, I'm joining or merging two data frame. Those are pred df and GT df. And I'm using left on ID class and right on ID and discourse type. And this is the outer join. That's why I'm passing how equal to outer. And yeah, suffixes are underscore pred and underscore gt. So this code does an outer join to ensure all predicted and ground truths rows are included in the resulting data frame. So an outer join returns all the rows from both data frames and combines them based on the specified columns, and any missing values in the column used for merging will be filled with NaNs, that is not a number. So here the left on and right on parameters are used to specify the columns from left and right data frame on which to merge, that is which column should be used as left join keys or right join keys respectively. And the suffixes parameter here is used to add suffixes to the column names to differentiate between the columns in the merged data frames. And in the pred df data frame, ID and class column represents the identifier and class of the predicted values respectively. And in the GT df data frame, ID and discourse type columns represent the identifier and class of the ground truth values respectively. So by using these columns to join the data frame, we can compare the predicted and ground truth values that have the same identifier and class. Next, I need to use the overlap this method that we just wrote earlier, overlap percentage here, to get the overlap between the two data frames. So here in this line, let me see. Okay, before that, I'm just applying fill NA to fill any of those empty things. Yeah, so here joined overlaps. This applies the overlap percentage function to each row of the joined data frame. And then the next two lines, I'm getting the actual values after applying the overlaps, because you know that overlaps will, these overlap percentage will give us overlap 1 and overlap 2, right? So that's what I need to get here in the next two lines. So I'm applying, making use of this eval method here. This function will evaluate to get the actual values from the tuple. For example, if I have a tuple of 0.4 and 0.6 as the first element and second element, it will be evaluated to the list of 0.4 and 0.6 with this eval method. And then you grab the first element with this 0 and grab the second element with 1. And that's my overlap 1 and overlap 2. So basically after these two lines, the joined data frame will have two new columns, overlap 1 and overlap 2, that respectively contain the overlap percentage between the ground truth and prediction and the overlap percentage between the prediction and ground truth. And remember now, according to the Kaggle's official page, that if overlap between the ground truth and prediction is more or equal to 0.5 and the overlap between the prediction and ground truth is more or equal to 0.5, that prediction is a match and considered a true positive. So that's what I'm going to calculate here. That is potential true positive. So I take joined overlap 1 more or equal to 0.5 and joined overlap 2 more or equal to 0.5. So if both are true, then that's a potential true positive. Similarly, going by this logic of theirs from Kaggle, that if multiple matches exist, the match with the highest pair of overlap is taken. And hence I need to also implement this logic as well. Multiple matches exist, the match with the highest pair of overlap is taken. So first I create this max overlap column in joined, and that will be from the joined data frame overlap 1, overlap 2, and take the max across axis 1. And then I need another array which is my true positive predicted IDs. And for that, I do this line, join.query. I run a query on potential TP column, then sort the values of max overlap column with descending order, that is ascending equal to false, and group by ID and prediction string GT. And then I apply dot first. So this dot first, this is because we want to keep only the ID with the highest overlap, because this is already sorted on a descending order. I just need the very first value or the very first row's value. And finally, these values method. So this will extract the pred ID values from the resulting data frame and convert them into a NumPy array. Thus, this final result, that is these TP preds IDs, contains an array of predicted IDs that are potentially true positives based on their overlap with the ground truth. So the true positives are taken care of with this line, but I also need to take care of the false negatives and false positives. And the Kaggle's competition rule in this respect was that any unmatched ground truths are false negatives and any unmatched predictions are false positive. So in this line, there I capture the FP pred IDs, which are P for P in joined, and from the pred IDs, I take all the unique values and only if P not in TP pred IDs. Sorry, I just messed up this. Yep. So if P is not in TP pred ID, so that's my FP pred IDs. And finally, matched GT IDs, that is matched ground truth IDs, will be, I run again join.query on potential TP column and then GT ID and unique. So here in this line, join.query filters the joined data frame to include only those rows where the potential TP column is true. That is where there is a potential true positive match between predictions and ground truth. And then I do this gtid.unique because I want to select the gtid column from the filtered data frame and return an array of unique ground truth IDs. And in case you have missed out on how this potential TP was calculated, this is the line. That is only when these two conditions are met, both the conditions are met, that's where the potential TP is true. And here in matched GTIDs, I'm capturing only that. And for the unmatched GTIDs, it's almost similar kind of query, C for C in joined GTID, and then take all the unique values. If C not in matched GTIDs. And then the rest of the calculations are easy. So my true positives is just the length of TP pred IDs, false positive is length of FP pred IDs, and false negative length of unmatched GTIDs. and then just calculate the F1 score. And if you are not familiar with this particular formula, it's actually the same formula. So F1 score, you all know, it's a 2 times recall multiplied by precision divided by recall plus precision. And here my recall is, the definition of recall is TP by TP plus Fn, and precision is TP divided by TP plus FP. So if you just replace these values in recall and precision in the F1 score, you will get this formula. And that's the return value from this entire function, that is this compute macro F1 score. And that's these macro F1 score is what we are going to use here, that is in the inference in the notebook. And the way that you invoke this function is just this little code. So all I'm doing is I get all the unique classes from my out of fold, and remember this out of fold is the result of after applying the this method, train predict calculation. What is that? Calculate preds. Yeah. So this out of fold, from this out of fold data frame, you get all the unique classes, and then just loop through the classes and get your preddf and gtdf. Your preddf is just out of fold.loc out of fold class equal to C, and then make a copy of them because you don't want to modify the original data frame. Similarly, you get gtdf and F1 score on those two df is just you get by applying this compute macro F1 score. And now this is the very final stage for this entire project. So I'm just going to do the inference on the test data and prepare the CSV file for the final submission to Kaggle competition. So first I'm just going to get all the, from all the test files, I'm just going to get the actual IDs of those files. So I create a list of files in the entire test directory with os.listdir, and then replace the .text part with an empty string for each of those files. And that's my all the test IDs. And so the final step for, remember this this F1 score we calculated, that is on the validation part of the data set. Because we folded the entire data set in 9:1 ratio, that is 9 part for training, 1 part for validation. So this F1 score was calculated only on the valid part. But now what I'm going to do is apply the trained model on the test part of the text files. So the Kaggle competition has already given us train directory and test directory, and now this final piece of work is only on the test directory because my model is fully trained. I have a trained model file, and only thing I need to do is apply that model on those test files, and all the test files are in .txt format. So first I need to do is I need the same things just like when we trained, that is I need the tokens and attention. So I'm creating these two arrays, test tokens and test attention, with initializing them with np.zeros, and the length will be, the shape will be len test id and max len, just like as we did previously for during the training part. And then before applying the model on the test dataset, I need to tokenize them. I need to read them and tokenize the text files before applying the trained model. So here in this block, that's what I'm doing. I'm running a loop for the entire length of my test IDs, and then I'm reading the name. This is my name, and then I'm opening them with open name r.read, and then this is the main thing, that is tokenizer.encode plus. So I am tokenizing the entire text of each file, and for max length, that's my parameter max len, padding max length, truncation true, return offset mapping true. And finally, I got my test token and test attention with these two lines. That is from the tokens, which will be the result after applying tokenizer.encode plus. I will get a dictionary, and one of the keys or one of the attributes of the dictionary is input IDs and attention mask. And those two I'm grabbing in these two lines. All right, so now I'm fully ready to apply the model. And so in the last section, I'm just doing model.predict, and to the model.predict, you passed your test tokens and test attention, batch size 16, verbose 2. And this will continue for some time, and finally it will print my p.shape, and my test spreads will be just like previously we did for train. I have to apply np.argmax to get the maximum values from these p tensor across the axis of -1. So this final variable test spreads will be used for the final evaluation of the model's performance by comparing its prediction with the ground truth labels. So what I need to do is get those prediction, and so we apply again the calculate spreads method just like we did for the training portion of the data. And only difference is this calculate spreads now takes the same arguments: tokenizer, target ID, map updated, max length, root D. Only difference is here. Then the text IDs, now it will be the test IDs, because now I'm only applying on the test dataset. And the spreads now will be test spreads, which is this variable right here. Dataset equal to test, verbose false. And that will give me my inference DF, which will be submitted as a final submission file to Kaggle Competition for checking with their internal test set. That is their internal ground truth, for which we do not have access to for the final leaderboard. All right, so now the final step is just make a CSV file from this inference DF, index false, and that's your final submission file that you will submit to the Kaggle Competition. And actually, after submitting these submission file, I got a leaderboard score of something like 6.670, which is not really on the top. This notebook was ranked something like 900 plus in the overall competition. But anyway, this is a baseline implementation. You can definitely do more feature engineering and more creative thinking on top of this. Probably that will be a subject of another video altogether. This was just an end-to-end implementation of Longformer on this Kaggle Competition. Alright, that's a wrap, and do stay tuned because I'm going to do quite a few NLP projects over the coming weeks and months on various Kaggle competitions and some of the famous models. So see you in the next one. Oh, forgot another thing, that the link of the entire code is in the description of this video, so do check out.